A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
I was looking at that footage from the car park in Jerusalem the other day, the one right near the Dome of the Rock, and it is honestly chilling how close that came to a global catastrophe. If that Iranian missile had been 200 meters to the west, we would be looking at a very different world today. The images of that crater just a stone's throw from one of the most sensitive religious sites on the planet really drive home the thin line between a regional skirmish and a total civilizational collapse. Today's prompt from Daniel is about that specific incident and the broader, often misunderstood reality of ballistic missile targeting errors. He wants us to dig into the physics of why these things land where they do, and whether we can actually nudge them away from critical sites, even when a full interception fails.
It is a heavy topic. Herman Poppleberry here, and Daniel is hitting on something that usually gets lost in the headlines. Most people see a missile hit a civilian area, like that car park, and they assume one of two things. Either the attacker is a total amateur who cannot aim, or they are a cartoon villain who specifically wanted to blow up a parking lot for some psychological reason. The reality is found in a metric called Circular Error Probable, or CEP. It is the fundamental way we measure the quality of a missile system, but it is a statistical concept, not a guarantee. When we look at the events of early 2026, we are seeing the limits of these statistics play out in real time over some of the most densely populated cities on Earth.
I think that is the first place we need to start because people hear the word error and they think mistake. They think someone typed the wrong coordinate into a computer. But in engineering, CEP is a design specification. It is an acknowledgement of inherent uncertainty. How do you actually define it for someone who is looking at a crater in a city and wondering how the missile ended up there instead of on the military base 10 kilometers away?
Think of CEP as the radius of a circle where 50% of your missiles are expected to land. If a missile has a CEP of 100 meters, and you fire 10 of them at a single point, 5 should land within that 100-meter circle. The other 5 will land somewhere outside of it. The catch, and this is what people miss, is that there is no hard limit on how far outside that circle they can go. It is a Gaussian distribution, a bell curve. You might have one that lands 500 meters away just because of a minor sensor vibration, a slight manufacturing defect in a control fin, or a sudden gust of wind in the upper atmosphere that the guidance computer could not compensate for in time.
So when we see a missile hit a car park 300 meters away from a sensitive religious site or a government building, that is not necessarily a failure of the guidance system in the way a layman thinks of failure. It is just the tail end of the probability curve. It is the math working exactly as intended, just with an outcome we do not like.
That is the grim reality of it. For the Iranian missiles used in the recent barrages, like the Fatah 1 or the K-bar Shikan, the claimed CEP is often around 30 to 50 meters. But those are test range numbers under ideal conditions, likely measured using GPS assistance on a clear day with no electronic interference. In a real combat scenario, like the ones we have seen throughout 2025 and into this year, where you are launching from a mobile platform, perhaps under extreme time pressure to avoid counter battery fire, and the missile has to travel over 1,500 kilometers, that effective error radius expands significantly. If the real-world CEP is actually 200 meters, then hitting a car park near the target is a statistical inevitability over a large enough volume of fire. You are essentially rolling a 20-sided die, and every once in a while it lands on the worst possible outcome.
It feels like we are talking about two different things here. Accuracy versus precision. I remember you explaining this to me years ago with a dartboard analogy, and I think it is worth revisiting because it clarifies why a missile can be high-tech but still miss.
It is a crucial distinction. Precision is the ability to hit the same spot over and over again, even if it is the wrong spot. If all your missiles land in the same car part 500 meters away from the target, you have a very precise system with a systematic bias. Maybe your map coordinates are slightly off, or your launch platform is not leveled correctly. Accuracy, on the other hand, is how close that group is to the actual bullseye. Most modern ballistic missiles are actually quite precise, but their accuracy is limited by the quality of their initial positioning and the drift of their internal sensors during flight. If you have a precise but inaccurate missile, you get a tight cluster of craters in the wrong place. If you have an accurate but imprecise missile, your craters are scattered all around the target, but the average center of those hits is the bullseye.
Let us talk about that drift. These things are moving at several kilometers per second. They are leaving the atmosphere, spending time in the vacuum of space, and then slamming back in. How does a missile actually know where it is once it is halfway through its journey?
Most of them rely on an inertial navigation system, or INS. This is a suite of accelerometers and gyroscopes that track every movement the missile makes from the moment it leaves the launcher. It is like trying to find your way across a dark room by counting your steps and timing your turns. It works, but errors accumulate over time. We call this INS drift. If your gyroscope is off by even a tiny fraction of a degree at launch, that error translates into hundreds of meters of displacement by the time the warhead re-enters the atmosphere 1,500 kilometers away. Think about it. A 0.1 degree error at the start of a 1,000-kilometer journey puts you nearly 2 kilometers off target at the end.
And that is why they try to use global positioning systems to correct it, right? But I assume in a conflict like the one we are seeing in 2026, the GPS signal is the first thing to go. We have seen reports of GPS interference affecting commercial flights from Cyprus all the way to Jordan.
The electronic warfare environment over the Levant right now is incredibly dense. Both sides are jamming and spoofing GPS signals constantly. If a missile loses its satellite lock, it has to fall back entirely on that INSS. This is where the older technology really shows its age. Modern high-end systems use stellar navigation, where a camera actually looks at the stars to fix its position, or terrain contour matching, but those are expensive and complex. If you are Iran and you are trying to overwhelm a defense system with quantity, you are likely using cheaper INS units that are prone to higher drift. This leads back to what we discussed in episode 1278 regarding the 14% doctrine.
Right. The idea that if you are using massive warheads, you do not need surgical precision. If your warhead is heavy enough, a miss of 100 meters still achieves the objective. But as we saw in the Jerusalem car park, that doctrine is terrifying when the target is in the middle of a holy city.
Precisely. In episode 1278, we talked about how Iran has shifted toward these heavy hitter warheads. When you have 1,000 kilograms of high explosives, your acceptable CEP threshold goes up. You are not aiming for a specific office window. You are aiming for a city block. But when you are aiming at a city as dense and as historically sensitive as Jerusalem, a 200-meter error is the difference between a military strike and a massive civilian tragedy that could ignite a world war. The physics of the end-stage re-entry is where it gets even more unpredictable. When that re-entry vehicle hits the thick part of the atmosphere, it is traveling at Mach 10 or Mach 12. The air in front of it is compressed so violently that it turns into plasma.
That plasma sheath is something we have touched on before, but I do not think people realize it is essentially a blackout curtain for the missile.
It is a nightmare for sensors. That plasma is electrically conductive, so it blocks radio waves and creates massive thermal noise. If the missile is trying to use an optical seeker or a radar to find its target in those final seconds, it has to look through a wall of fire. Any slight asymmetry in the shape of the warhead, maybe a bit of heat shield that charred unevenly or a tiny piece of debris that stuck to the nose cone, will create aerodynamic lift. At those speeds, that lift pushes the missile off course in ways the internal computer might not be fast enough to correct. This is why sub-100-meter accuracy at intercontinental ranges is one of the hardest engineering challenges in human history.
You mentioned aerodynamic lift, which makes me wonder about Daniel's question regarding deflection. If total interception is not possible, maybe because the defense system is overwhelmed or the interceptor misses, is there a way to nudge these things? Can we make a missile that is headed for a hospital land in an empty field instead?
This is a fascinating area of electronic and kinetic warfare that has seen a lot of development in the last 2 years. There are two main ways to approach this. The first is electronic disruption, or spoofing. If the missile uses a radar altimeter to decide when to detonate or an optical sensor to refine its path, you can feed it false data. This is more than just jamming, it is about taking control of the missile's perception. If you can trick the missile into thinking it is 500 meters higher than it actually is, or that the landmark it is looking for is slightly to the left, you can induce a steering command that shifts the impact point.
But that assumes the missile is smart enough to listen. If it is just a dumb INS projectile following a preset ballistic arc, you cannot really talk it out of hitting its target. It is just a falling rock at that point.
In that case, you have to get physical. This is what some engineers call terminal disruption. It is different from a standard interception where you try to blow the warhead into 1,000 pieces. Instead, you might use a high-powered laser or a close-in weapon system to damage just one side of the reentry vehicle. If you can change the aerodynamics of the warhead even slightly, the air pressure at those speeds will do the rest of the work for you. It is like sticking your hand out of a car window at 80 kilometers per hour. If you tilt your hand, the wind pushes your whole arm. At Mach 10, that effect is magnified by orders of magnitude. A tiny bit of damage to a control fin or the ablation of a small section of the heat shield can pull a missile hundreds of meters off target in the final 3 seconds of flight.
That sounds like a double-edged sword, though. If you nudge it, you might be saving the primary target, but hitting something else entirely by accident. You're essentially playing a high-stakes game of billiards with a 1-ton warhead over a populated area.
It is a moral and tactical nightmare. If the missile is headed for a government building and you nudge it and it hits a residential apartment block instead, did you succeed? This is why the military prefers kinetic kill vehicles that hit the target head-on and try to vaporize the warhead mid-air. But as we discussed in episode 936, even a perfect hit creates a massive debris field. You are still dropping several tons of hot metal and unspent fuel on whatever is below the interception point. There is no such thing as a clean kill in the atmosphere.
I think people have this image of missile defense as a shield, like a literal physical dome that things bounce off of. But it is more like a shotgun blast hitting a clay pigeon. The clay pigeon is gone, but the shards are still falling. In the Jerusalem case, there were reports that the car park impact might have been a diverted missile or the result of a partial interception. When you look at the crater, what does that tell you about the state of the warhead when it hit?
Looking at the telemetry and the imagery from that site, the crater was significant, which suggests the main charge actually detonated, or at least the kinetic energy was fully preserved. If it had been a successful interception, you would expect to see a more scattered debris field and a smaller, less uniform crater. The fact that it was a single, massive impact near such a sensitive site suggests that the missile's guidance simply failed to account for the final atmospheric variables, or the INS drift was just that large. It is a reminder that in the age of ballistic warfare, the margin of error is often larger than the target itself.
It also highlights the shift in doctrine we have been seeing. If you are the IRGC and you know your CEP is 200 meters, you are not aiming for a specific office. You are aiming for a zip code. You are using the statistical error as a feature, not a bug. It creates a psychological effect where no one feels safe because the missiles are essentially random within a certain radius.
It is a return to the V2 rocket logic of the Second World War. The Germans knew they could not hit a specific factory in London, so they just aimed for the city center. The math has improved since then, but the principle remains. If your goal is to project power and create chaos, a missile that misses by 300 meters is just as effective as one that hits the bullseye, as long as it hits something that makes the news. In fact, a miss can sometimes be more politically destabilizing than a hit on a military target.
What about the future of this? Daniel asked about mitigating impact. Are we seeing new technologies that can take control of a falling warhead? I have read about some experimental systems that use high-power microwaves to fry the internal electronics of a missile as it descends.
High-power microwave, or HPM, is the holy grail of terminal defense. Unlike a laser, which has to stay focused on a single point to burn through the casing, a microwave pulse can saturate a large area. It finds its way through every seam and every vent in the missile's skin and induces a massive current in the circuit boards. It basically lobotomizes the missile. If the guidance computer dies, the control fins usually lock in their last position or go neutral. Depending on the design, that usually results in the missile tumbling, which increases drag and can cause it to break up before it even hits the ground.
So you're essentially turning a guided missile back into a dumb rock. That seems like the safest bet if you cannot guarantee a clean midair explosion. At least, a tumbling, breaking missile loses a lot of its kinetic energy and is less likely to trigger its primary fuse correctly.
The challenge is the timing. You have a window of maybe 5 to 10 seconds to engage a re-entry vehicle in the terminal phase. Your sensors have to be incredibly fast and your tracking has to be perfect. This is why the Shield of the Levant architecture we talked about in episode 1392 is so focused on layered defense. You want the Arrow 3 to hit it in space, the Arrow 2 to hit it in the upper atmosphere, and then systems like David's Sling or specialized electronic warfare units to handle the leftovers in those final seconds. The car park incident was likely a failure in that final layer, or perhaps a deliberate decision not to engage, because the trajectory was calculated to hit an empty area, only for the atmospheric drift to pull it back toward the city.
It really changes the way you look at those videos of interceptions over Jerusalem or Tel Aviv. You are not just seeing a hit or a miss. You are seeing a massive multi-billion-dollar mathematical battle to shift a probability distribution away from people and toward empty space. It is a game of inches played at Mach 10.
And that is the key takeaway for how to read the news on this. When you hear that a missile fell in an open field, that is often not luck. It is the result of a defense system successfully nudging or disrupting the target just enough to move the impact point out of the red zone. On the flip side, when a missile hits a car park, it is a reminder that no system is perfect. You are fighting against the laws of physics and the inherent chaos of reentry. We have to view these events through the lens of probability. A 99% success rate still means one missile gets through every 100 launches.
I think we also need to address the debris problem one more time, because that is what really scares people. Even if you hit the missile, you are still dealing with the falling interceptor and the fragments of the warhead. In a city like Jerusalem, where everything is built of stone and the streets are narrow, even a small piece of debris falling from 20 kilometers up is lethal.
A 1 kilogram piece of steel falling from the edge of space reaches terminal velocity very quickly, and at that speed, it has the kinetic energy of a heavy caliber bullet. Now multiply that by thousands of fragments. This is why the Israeli Home Front Command is so adamant about people staying in shelters even after they hear the boom of an interception. The boom is just the start of the danger phase. The rain of metal follows 30 to 60 seconds later. In the car park incident, even if the main warhead had been destroyed, the engine block of that missile, which is a massive piece of steel, would still have crashed down somewhere. If that engine block hits a car, it looks exactly like a missile strike to the person standing next to it.
It is a sobering thought. We have spent decades trying to make missiles more accurate, and now we are spending just as much effort trying to make them predictably inaccurate when they are headed for us. It is a constant arms race between the CEP of the attacker and the deflection capability of the defender.
The next leap in this is going to be AI-driven terminal guidance. We are starting to see warheads that have enough onboard processing power to run real-time computer vision. They look at the ground, compare it to satellite imagery, and make micro adjustments to the fins to steer themselves in the final seconds. That effectively brings the CEP down to near zero, but it also creates a new vulnerability. If the missile is relying on what it sees, you can use smoke, mirrors, or even high-intensity lights to blind it. We are moving from a battle of physics to a battle of perception.
If you can make the missile's brain lie to it, you can win the fight without ever firing a physical interceptor. But we are not quite there yet for the mass-produced ballistic threats. For now, we are stuck with the math of the Gaussian curve and the hope that our defense systems can nudge the outliers into the dirt. It is a reminder that as much as we like to think of war as a series of intentional acts, a lot of it is just the chaotic interaction of high-speed hardware and statistical probability.
It is why the data points Daniel is looking at are so important. Every impact, every miss, and every interception is a piece of a larger puzzle. We are learning the signatures of these missiles, how they drift, and how they react to disruption. The Jerusalem car park hit was a tragedy of near misses, but it was also a massive diagnostic event for the engineers who build the shields. They are looking at that crater and reverse engineering exactly what went wrong in the guidance loop.
It feels like the main takeaway here is that we should stop viewing missile accuracy as a binary hit or miss. It is a cloud of probability. When you are standing in a city under fire, you are standing inside a statistical model. The goal of the defense is not to erase the cloud, but to move it.
That is the most accurate way to describe it. You are trying to bias the results of a high-speed, high-stakes experiment. And as the technology on both sides improves, the size of that cloud shrinks, but the stakes for every meter of error only go up. We have moved from a world where a miss was a mile to a world where a miss is a car park, and in a place like Jerusalem, that is still too close for comfort.
Well, I think we have thoroughly deconstructed the car park incident. It is a lot more complex than just a bad aim or a lucky break. It is the intersection of INS drift, plasma physics, and terminal electronic warfare. It is a reminder that the future of warfare is as much about managing math as it is about managing metal.
It is the kind of stuff that keeps engineers up at night, and for good reason. The math is beautiful, but the consequences are anything but. We are living in an era where the difference between a headline and a history book is a few degrees of sensor drift.
Thanks as always to our producer, Hilbert Flumingtop, for keeping us on track and making sure we do not drift too far into the weeds ourselves.
And a big thank you to Modal for providing the GPU credits that power the research and processing behind this show. We could not do these deep dives into ballistic trajectories without that kind of horsepower.
This has been my Weird Prompts. If you found this dive into the physics of missile defense useful, or if it changed how you look at those news reports from the Levant, we would love it if you could leave us a review on your podcast app. It really helps other curious minds find the show. Check out the archives for those episodes we mentioned, 936, 1278, and 1392, for the full technical background.
We will be back soon with more of Daniel's prompts. Until then, stay curious, stay safe, and keep an eye on the data.
Goodbye for now.
See you next time.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, my weird prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My weird prompts, that's the flows from sloth